listen to the third Dr. Arvind Bhatnagar Memorial Lecture in a short time. So I would, in the audience, this is the first time actually we are organizing it offline. And in the audience, we have almost the whole PRL, along with
Hello.
Professor Anil Bharadwaj, Director PRL, Professor Pallam Raju, Dean PRL, Professor Deshpande, Registrar PRL, and all my colleagues and senior colleagues and junior students. So, kind of welcome to you, everyone. And here also in the audience at USO, we have not only USO faculties, but academicians from in and around all the prestigious institutes of Udaipur, including MLSU. So, thanks to you for being here. So, with that, I would like to request Professor Anil Bharadwaj to welcome the speaker formally and initiate the program. Sir, please.
Hello, can you hear me? Hello, can you hear me?
Yes, we can hear you, but if you can speak a little louder.
Still louder?
Now it is okay, sir.
It's better now?
Yes, sir, better now.
Okay. So, namaskar, susagatam, em cho, ram ram, kambagadi, adabars. A very good afternoon. मैं अनिल भारद्वाज आप सभी का तीसरे डॉक्टर अरविंद भटनागर मेमोरियल लेक्चर में स्वागत करता हूं, अभिनंदन करता हूं. I, Anil Bharadwaj, very warmly welcome all of you to the third Dr. Arvind Bhatnagar Memorial Lecture. We started this series of lectures in the memory of Dr. Arvind Bhatnagar in the year 2021 as a part of the PRL's Pratham Jubilee celebration. This Dr. Arvind Bhatnagar Memorial Lecture is dedicated to the memory of late Dr. Arvind Bhatnagar, the founder of Udaipur Solar Observatory, and his immense contribution which he has done to the solar physics research in India. So essentially this lecture commemorates the rich history and the growth of solar physics in the country through Udaipur Solar Observatory. This lecture is organized every year in the month of November, which is close to the birth date of Dr. Bhatnagar, which is 19th of November. We are extremely pleased and delighted to have the third Arvind Bhatnagar Memorial Lecture speaker with us today, Professor Helen Mason. And she is from University of Cambridge in UK. And she is there with us today in person in Udaipur, because this is the first time we are having this lecture in person. Earlier two lectures were online because of the COVID issues. I really thank Professor Helen Mason for agreeing to our invitation and to be with us today in person in Udaipur. May I now request Dr. Nandita Srivastava to tell us a little bit more about Dr. Arvind Bhatnagar before we go on to Professor Pallam Raju to introduce the speaker. Over to you, Professor Nandita Srivastava.
Good afternoon, everyone, and thank you, Professor Bharadwaj. This one?
I need to unmute it.
Yeah.
Now it is unmuted.
Yeah, we can hear you now.
Can you hear me?
Yes, yes.
Okay. So thank you, Professor Bharadwaj. It's really an honor and privilege for me to present to you the legacy of Dr. Arvind Bhatnagar and the significance of this memorial lecture. Dr. Bhatnagar's life is a testament to his unwavering dedication and pioneering spirit in the field of solar physics. From humble beginnings in Byawar, where he was born, journey as a scientist. After obtaining his master's degree in physics from Agra University, his academic pursuits took him to various observatories across the globe, including Kodaikanal, where he did his PhD under the able guidance of Dr. M.K. Venubapu. And of course, later on, he moved to Nainital, which was UP State Observatory then, Aries as we know now. He then moved to prestigious institutions in the United States, where he gained his expertise in solar astronomy while he worked as a Carnegie Fellow in Mount Wilson and Palomar observatories. And then he later moved as a resident astronomer at the Big Bear Solar Observatory of the California Institute of Technology, Pasadena till 1972. On his return to India, his visionary leadership and has led to the establishment of the Udaipur Solar Observatory in 1975 in a small island in the Lake Fateh Sagar. It is unique because he carefully chose this island for its conducive conditions for solar observations. Under his guidance and leadership, the Udaipur Solar Observatory has flourished, as you see now. It has become a global center for high-resolution solar observations. It became important for the global and well-known for Global Oscillation Network project, significantly contributing to helioseismology research. The Gong instrument, as many of you know, has been operating in Udaipur for more than 25 years now. In 1993, he recognized the importance of helioseismology research and organized the first tutorial workshop in PRL Ahmedabad. This pioneering initiative triggered a spark of interest among researchers in India in the scientific community, and subsequently it led to smaller groups in USO, in TIFR, and in IIA, who began to actively explore this new area of helioseismology and started research. Dr. Bhatnagar's research interest focused on different aspects. If you look at his publications, you'll find papers on sunspots, filament eruptions, flares, and solar oscillations. So he has covered a lot of topics, which resulted in around 80 publications. He has also authored a fascinating book, which many of the students here have studied, which is Fundamentals of Solar Astronomy. Acknowledging his outstanding contributions, Dr. Bhatnagar was elected a Fellow of the National Academy of Sciences in India, Allahabad. He also played a crucial role in the formation of the Astronomical Society of India as one of its founding members. Beyond academia, Dr. Bhatnagar's visionary leadership was evident as the founder director of the Nehru Planetarium, which is in Mumbai. And subsequently, he served as advisor to many of the planetaria in the country, like Jawahar Planetarium in Allahabad, Baroda, Sardar Patel Planetarium, and Nehru Planetarium in Delhi. It is also worth mentioning that Dr. Bhatnagar's commitment to popularizing astronomy was extraordinary. Some of you might be aware that during the 1995 solar eclipse, total solar eclipse, he achieved an unparalleled feat, supervising the capturing of the image of the solar corona from an Indian Air Force plane, that is the MiG-25, which was cruising at an altitude of 25 kilometers, and he chased the eclipse's path. As some of you also may be aware, he was very actively advocating for environmental and lake conservation in Udaipur. He was appointed as one of the High Court commissioners for conservation of lake system in Udaipur. And in 1996, he started a novel project called SUCHI, which stands for Swachh, Healthy, urban clean and hygienic environment abhiyan in several localities in Udaipur for solid waste management through public participation. So these efforts show his multifaceted commitment to the society and to the science both. On a personal level, I would like to mention that I had the privilege to work under his supervision for my PhD. And to honor his legacy, we organized this annual Dr. Arvind Bhatnagar Memorial Lecture, which Dr. Bharadwaj has already explained, in the month of November, which is close to his birthday, that is 19th November, for his exceptional contributions in solar physics and his indelible mark on the scientific community and society. I'm actually very delighted to have my friend and very distinguished speaker, Dr. Helen Mason, to deliver this third Arvind Bhatnagar Memorial Lecture today, who herself is an extraordinary public educator and an extraordinary solar physicist. So with these words, I would like to end and invite Dr. Ramit Bhattacharya for further conducting the program. Thank you.
Thank you, Professor Srivastava. I would like to request Professor Pallam Raju to introduce the speaker.
Okay, thank you, Ramit. I hope I'm audible.
Professor Pallam Raju.
Yes. It's indeed an honor for me to introduce today's speaker of the third Arvind Bhatnagar Memorial Lecture, Professor Helen Mason. Professor Mason is a solar scientist at the University of Cambridge. Her field of research is solar physics, in particular the ultraviolet and the X-ray spectrum of the sun. She has worked on many projects jointly with UK, NASA, ESA, Japanese and ISRO's projects, including the Solar Heliophysics Observatory, SOHO, Hinodi, Solar Dynamics Observatory, and the XSM, which is the Chandrayaan-2's X-ray solar monitor. Recent solar space observations have completely changed the view of our sun, and especially NASA's Parker Solar Probe and ESA's Solar Orbiter are traveling closer to the sun than ever before to improve our understanding of the sun, the solar wind, and its interaction with the Earth's environment. ISRO's Aditya L1 mission, which has been launched in September 2023, is also cruising into the Lagrange 1 point and is expected to provide some very exciting results. Professor Mason has always been keen to convey her passion to solar physics to the public and to the students. She has given many public lectures and worked closely with schools. She has participated in several radio and TV programs, for example, BBC 4's Seven Angels of Starlight and BBC R4's In Our Time, the Solar Wind in 2020. Professor Mason works closely with teachers and students throughout the UK, most recently leading the project called sunspaceart.org, which is funded by STFC and which brings in the artists and scientists together and to encourage the theme of STEAM, where the A is for arts, STEM plus arts, which is a very interesting venture indeed. In 2014, Professor Mason was awarded an OBE, which is the Order of the British Empire, for her services to higher education and to women in science, engineering and technology. In 2018, she was awarded the Royal Astronomical Society's Annie Maunder Medal for outreach. In 2020, the Sun Space Art team won the Arthur C. Clarke Group Award for space achievements in education and outreach. With this brief introduction, I will now invite Professor Helen Mason to deliver her lecture on the reaching for the sun. Professor Helen Mason, please.
Yeah, I think we can hear it. Yeah, wait.
Is the microphone working?
Yeah, it's good.
Yeah, microphone's working. Okay, we've had some challenges with technology today, but I think we have everything working. Can everybody hear me? I hope everybody in the room can hear me, but I hope everybody, there's some seats here at the front if people want to sit down. It's a great honor to be here. And I work closely with colleagues in India on ISRO space missions, and have been visiting India for many years. So it's a great honor to be here. And it's also a great honor to be talking to many people, not just the people here in the audience, but at PRL and other places. And I'm very happy to see so many young faces in the audience here. This morning, I had a very good engagement with the young people here, the students and the postdocs, and they shared with me the work that they were doing, which I was very impressed, a very wide range of work. So thank you for this honor, for inviting me to give this very special lecture. I feel very honored to do this. I have worked in solar science on many solar space missions, and I will start by just giving you a flavor of what my work is. And then I want to move on a little bit of spectroscopy. I'm an expert in spectroscopic observations of the ultraviolet and the X-rays, and then tell you a little bit about the most recent missions to the Sun, the Parker Solar Probe, Solar Orbiter, and also then some very interesting work I've been doing with my colleagues at PRL on Chandrayaan-2, the X-ray solar monitor. Been working together during lockdown regularly, and it's been a very, very productive time. And that's my reason for being here, is to visit my colleagues at PRL. So let me start. Slides forward. So you can't use this one?
Sure.
Okay, just right. Okay, yeah, now. Okay. So these are just recent solar space missions, starting from SOHO, which was launched over 20 years ago. But I actually worked on Skylab. I'm that old. I worked on Skylab and Solar Maximum mission before then. And I've been honored to work on many of these missions, which are NASA, ESA, the European Space Agency, Japanese missions, and more recently with my Indian colleagues on ISRO missions. Obviously, I'm not going to talk about all of these, I just don't have time, but I am going to cover a few aspects of some of them, which I'd like to introduce to you. Most recently, of course, Chandrayaan-2 was launched in 2019, Parker Solar Probe in 2018, Solar Orbiter 2020, and we've just had an amazing launch of Aditya L1 in early September. And it's close to the Lagrange point now, but by January, you'll be hearing a lot more about the results from Aditya L1. So I don't work in isolation. Teams are very important in any space projects, in scientific endeavors. I'm sure here at Udaipur too, everything, you work with other people who have expertise and skills in different areas, technicians, operators, software people. And here's a team, my team. So these are members of my group, and you might recognize here Durgesh Tripathi, who worked with me as a postdoc for many years and now has his own group at IUCAA. So we've worked closely together. Saga Mulle here came over from IUCAA. She was at Ferguson College. She worked at IUCAA for a while, and then she came and did a PhD in Cambridge with me. And then she went back to IUCAA. So other students and postdocs are now working around the world. Many are professors in the USA. Peter here and Steve are professors in the USA. And this man here, Giulio Delgana, I want to give a special mention. He's worked in my group for many years. And in fact, I retired in 2017 officially, although I'm still working, as you can tell. but he now heads the Atomic Astrophysics Group, which is the group that I head there. He sadly can't be with us for various personal reasons, but he has visited PRL on 2 occasions, I think, previously. Perhaps not Udaipur, but maybe he can do that on a future occasion. So I wanted to go back in time a little bit to Galileo. Why? Because I love Italy. Italy is another place that I love. And this is a view from Galileo's house, where he was kept under house arrest for his beliefs or his convictions and his observations of the planets, which confirmed Copernicus's proposal that for a heliocentric universe. But he also studied the sun, and these are his actual drawings of the sun. He projected an image of the sun, and here you can see the sunspots, and he said these sunspots had been seen in ancient days by the Chinese in the early morning fog, but he said these sunspots are actually on the surface of the sun. And again, that was very heretical. It wasn't accepted because the sun and stars were supposed to be perfect. So here he was saying that they were not perfect. And here you can see the rotation of the sun was about 25 days at the equator, obviously a little slower at the poles. If we look at the surface of the sun, we have the convection layer just beneath, and these are the most recent observations from a telescope called DKIST, which is in Hawaii, operated by the National Solar Observatory in the USA. And these are perhaps the most detailed observations, together with the Swedish telescope, that we have of the surface of the sun. And you can see the fine detail there. You look at the sunspots. This is a sunspot image from seen from DKIST, from this DKIST telescope. So many solar scientists are now using observations from DKIST, and it will also have coronal instruments, infrared instruments on it as well. And here we can obviously see when the sun is very active, as it is today. Today, I had a journey across to the telescopes, and we were able to see an image of the sun, and it was very spotty. It's not unlike the picture here. At the moment, we're in an era where the sun is very active, and there are a lot of sunspots. And of course, when we get a lot of sunspots, we get a lot of activity, and we get some beautiful aurora. And I think even in India, the aurora has been seen down to quite low latitudes recently, lower than normal. India has some amazing solar observatories and other observatories, and these are just some of them. Udaipur here, which I visited in 2014, honored to visit. Other observatories, Kodaikanal, which I haven't visited yet, in Tamil Nadu, which I would actually quite like to visit one day, perhaps, and obviously Aries and the National Large Solar Telescopes. So in 2014, we saw the MAS, the Multi-Application Solar Telescope, was just beginning operations. And this is an image from that telescope. I think it was probably officially opened maybe in 2015, but we were privileged to actually, it was being tested, it was being commissioned at that stage to actually see some images from it. That right? Yeah. Agreed, yes. And here, Nandita is showing me some very old catalogues of sunspots and activity that you have here at Udaipur. So it's a great honor to visit in 2014, and Jerry was here as well as Santosh. See Santosh at the moment, and we enjoyed it so much. So this time, when I knew that I was visiting PRL, when we arranged the visit, I said, please, can we go and visit Udaipur again? Because I enjoyed seeing the observatory, but I also enjoyed the interaction that I had with the young people who were here at that time. Obviously, the Indian observatories are very famous, and the Evershed effect, as we've heard earlier on from the students, it's discovered at Kodaikanal Observatory. Another of my very favorite astronomers, scientists, mathematicians is Sir Isaac Newton. Of course, he lived and he worked in Cambridge at Trinity College. Although, like us with COVID, there was a period when they had the plague and he had to, all the students had to evacuate from Cambridge and everywhere else and go home. And he went to Woolsthorpe Manor, where actually that was where he did some really interesting work. I think he was peaceful there, he was away from everything, and he had time to think, and that's where he developed the laws of gravity. But he was also very interested in telescopes. He made the reflecting telescope himself, he ground the mirrors himself, and when somebody said, well, why did you do all that work yourself? And he said, well, if I hadn't done it myself, it never would have been done. But he was interested in the colors of light and the colors of visible light, and did some experiments and on that, and showed that the visible light is made up of the different colored frequencies. As I said, my interest is in spectroscopy. So if we use a slit, we can then break down the light into its different components for different elements: hydrogen, helium, nitrogen, neon, argon, mercury. And we see that each of these elements have their own fingerprint or bar chart. I mean, we use bar charts now in supermarkets, or we use with our iPhones, we can get information from charts and things, and it gives us the information we need to know about the sun and the stars. And helium, of course, was discovered on the sun, and here's an image taken from Skylab of in a helium line. But not only does it give us information about the element composition of the distant astrophysical objects, but it also gives us much more information about density, about the temperature, about the movement shifts. Total eclipse of the sun. I'm not sure how many people here have experienced a total eclipse. I think it was quite a long time since there was one in India. When was the last one in India? Yeah, you saw that one?
5 or 6.
Yeah, it's a beautiful phenomena. And when you have a total eclipse of the sun, the moon precisely blocks out the disk of the sun. So the disk of the sun is 1,000,000 times brighter than the solar corona, the crown of light around the sun, solar atmosphere, which here, because it's ionized, traces out the magnetic field. So you're actually seeing the magnetic fields on the sun. Now, when they used a spectrometer to analyze the light from the sun, what they found was there were some unexpected emission lines in the green and in the red, and also in the yellow, in 530 nanometers or 5303 angstroms. And it took a long while to actually determine what these emission lines were due to. First of all, they invented an element called coronium because they'd had such a lot of success with helium. Helium is named after the sun, Helios. And they thought, well, coronium, but obviously that was one of those scientific theories that just ended in a dead end, didn't go anywhere. It couldn't fit it into the periodic table. And what they realized after a lot of careful work is actually the corona is 1,000,000 degrees. And at 1,000,000 degrees, what would be neutral iron is highly ionized. So for example, iron, which normally has 26 electrons, has 13 of those electrons stripped off because the atoms are bumping into each other. Work on this was done by Helen and Grotian and in Sweden, and they did very careful laboratory measurements of the wavelengths and extrapolated these back to realize that this red line and this green line is due to transitions in the ground configuration of these two ions. Now, why am I interested in these? Well, I find solar corona and eclipses fascinating, but also I did my graduate work in London at University College London, and my professor here, Professor Mike Seaton, was a very eminent atomic physicist with a big atomic physics group, and he was applying the atomic physics that we were doing to different aspects, to the sun, to supernova, to all sorts of different astrophysical applications. And he asked me, when I started my graduate work, to look at some eclipse observations. In fact, it was the 1952 eclipse, and he asked me to analyze these eclipse observations and do some atomic physics calculations relating to those observations. In fact, these were the first calculations of any accuracy which were done for these coronal ions. So atomic physics programs had been developed at University College, and working with other colleagues, I was able to calculate all the atomic physics parameters we needed to understand the intensities of these lines. Sitting with him here and talking to him is Dr. Alan Burgess, who is another very eminent atomic physicist and astronomer. And he worked on a process called dielectronic recombination, which is important in the recombination and ionization processes within the plasma. Now, he worked in London for a while with Professor Seaton, but actually then he moved to Cambridge. And when I moved to Cambridge, he supervised my work as a postdoc at Cambridge. So I joined his group. So if we look at emission from the green line and emission from the red line, and this is during an eclipse, what we find is we've got very hot, the green is slightly hotter, about 2 million, and the red is about 1 million. And we can see quite clearly regions of different temperature in these eclipse observations. Now, I've been very honored to actually have seen 3 total eclipses, one in 1998 in Guadeloupe in the Caribbean, which was amazing, one in the UK, which is very unusual. We just happened to be in a position in the Channel Islands where we were able to view it. And then during the 2017 eclipse, I was NASA's solar expert at the Great Smoky Mountains National Park, which was a real thrill. And also we had engagements, activities, storytelling, dancing. Now, the Cherokee Indians used to live and still do live in the Great Smoky Mountains. And they have, like, if you don't understand the science, sometimes you make up stories. And their story was that a giant frog is eating the sun during an eclipse. So that's their giant frog. Now, of course, if you look not in the visible, but if you then go beyond the visible and look in the X-rays or the ultraviolet, this is what the corona looks like from Yoko, a Japanese satellite, in the X-rays. And you'll see there are dark regions in the corona where the magnetic field is open, and there are bright regions where the sunspot regions are. And what you're seeing there is just plasma at 1 million degrees. Go from solar minimum to solar maximum, because we know the sun has an 11-year cycle. The X-ray emission is very different. So here, there's very little X-ray emission in solar minimum and a lot of X-ray emission in solar maximum. Now we can look at spectral lines, which are not just in the visible, which is what I calculated. In order to calculate these, I had to take a lot of energy levels. And if we come down from higher energy levels, we get spectra in the ultraviolet. So this is an old spectrum, rocket spectrum, a very good one in the ultraviolet from 160 to 220 angstroms. And you can see lots of lines from iron, from silicon, from oxygen, from different ion stages, different elements. So as I said, in the 70s, late 70s, I moved to Cambridge and worked with Dr. Alan Burgess. And this is the old building. We started off in a very old building in Cambridge, the Department of Applied Mathematics and Theoretical Physics. And this is our new mathematical building, the Centre for Mathematical Sciences, which now comprises both applied mathematics and pure mathematics and statistical financial mathematics as well. So for the students here who are interested in spectroscopy and in different spectroscopic diagnostic techniques, I would recommend a review that Giulio Dalzano and I wrote in 2018, which gives a lot of information, historic context. It defines a lot of the plasma parameters that we derive and how we derive them, and also discusses non-equilibrium processes and non-Maxwellian processes. So I'm just going to very briefly say a couple of words about this. Obviously, when we get an emission line, we go from an upper level to a lower level, and a photon of light at a particular wavelength is emitted, a particular energy. From this, the intensity of that line, we can express it in the form of the abundance, the element abundance, and this G of T, which is basically some atomic physics parameters that need to be calculated for the particular ion that we're looking at. And then the electron number density and integrated along the line of sight. So this G of T is expressed in the form of different atomic parameters. This is the transition probability. This is the amount of level J, population of level J relative to the whole ion. And this is the ionization state of that particular ion. And we need to calculate all of these processes. We need to calculate all of the atomic processes that excite the level and de-excite the level. And we can then derive an expression. If we make a couple of approximations, we can derive an expression which we call the emission measure. And that's really basically the amount of material at different temperatures. We use that quite a lot to compare the theoretical models that predict a particular emission measure with what we observe. Here we've got a range of ions for ion over temperature at the bottom from 10 to the 6 to the 10 to the 7. And as you can see, as we increase the temperature, then we strip more and more electrons off. So we get highly ionized iron up at 10 million degrees. We've got iron 21, iron 20. We've got iron which has been, the number of electrons has been stripped right off it. So iron 10, for example, when we talk about it, unfortunately, like many things, there's confusion because we use two different types of notation. Atomic physicists would write it as Fe plus 9, that's 9 electrons stripped off. Spectroscopists would write it as Fe10 in Roman numerals. So we have to have a language exchange there. But that would be formed at about 1 million degrees, around about here. And then as you go up in temperature, so you go up in ionization stages. And this enables us to determine what the temperature is for the plasma that we're looking at. Now, in order to look at all these different ion stages, all these different elements, we need a vast amount of atomic data and to do calculations, detailed calculations, quite complex calculations. And I wanted to mention my colleague, Anand Bhatia, who works at the Goddard Space Flight Center, and I visited him recently last month, and other colleagues at NASA's Goddard Space Flight Center. And we worked together with the codes from University College London, and we calculated atomic data for many of the ions that are seen in the solar corona and that are also seen in other astrophysical objects. So let me briefly mention some of the projects and just briefly mention some of the work. So Solar Maximum mission was launched in 1980, long time ago, well before many of you were born. And it was operated, these missions are operated from the Goddard Space Flight Center, where we all gathered together and decided what we wanted to observe and what sequences we wanted to run. And I worked with two teams, so I was a co-investigator with two teams. One was a UV spectral polarimeter, UV instrument, and the other was an X-ray telescope, which had a flat crystal spectrometer and a bent crystal spectrometer. The Solar Maximum mission sadly failed after a couple of years, or quite quickly actually, and it had to be repaired by astronauts going up on the International Space Station. So if we just briefly look at some of these spectral lines, this is very high ionization stages, around about 1.65, 1.8 angstroms. So the higher the energy jump, the shorter the wavelength. So we go down to very short wavelengths. You can see lots of different lines from different stages of highly ionized ion. Now, what we saw sometimes when we looked at these lines were slightly shifted. And a blue shift indicates that plasma is moving towards you. So they saw blue shifts, and these are flares. You get these lines when you get solar flares. So you get temperatures going up to 10 million degrees. And we then saw a slight blue shift in the line. Now, one proposal was that when you had a solar flare, you had some reconnection higher up, and then you had particles or energy going down into the foot points. And then you get a process called chromospheric evaporation. You get particles evaporating up very high, they get heated and they're evaporating up at very high temperatures. And that's something that we've been studying, but we weren't quite sure whether this model was correct. And we needed quite a lot of work to reinforce the model arguments for it. With this crystal, we're just seeing the full disk, so it's very difficult to spatially resolve different elements of it. However, with the other instrument, the UV instrument, we did have spatial resolution. So we were able to look at the shift in a line, which is actually from iron 21, so it's highly ionized, but it's formed at, in the UV, 1,354 angstroms. And because it's formed in the UV, we can see the width of the line. The width of the line is just a Gaussian according to the peak temperature it's formed at, a little bit more actually, but we can also see the shifts in the line. Because we have chromospheric lines, we're able to measure those shifts and calibrate the wavelength shifts. Without chromospheric lines, it's very difficult to do that. And from this, we were able to determine that this blue shifted material in this very high temperature line during the impulsive phase of flares, it's the very beginning of the flares, came from the flare foot point kernels. Now, around about 1 angstrom again, around 1 to 2 angstroms, 1.8 angstroms, we see lots of interesting lines from other highly ionized iron species. These lines, we see what we call the strongest line, but these lines are actually interesting set of lines called satellite lines. So we say we've got a helium-like transition here, which is the basic transition. If we add an extra electron on here, here's a 2p added onto that, 2s added onto that, what we get is a set of lines which almost mimic them. They're very close in wavelength, and they're called satellite lines. And we can use those for different diagnostics because they're formed in slightly different ways. They can be formed by dielectronic recombination in other ways. So they're very interesting to be able to use those. This is an X-ray spectrum around about 10 to 12 angstroms. And again, you can see a whole sequence of iron lines. This is with the flat crystal spectrometer. And working with my colleagues, Ken Phillips, who was at Goddard, we were able to analyze these lines. And looking at some of the transitions, we were able also to determine the electron density. Now, I'm not going to go into the details of how we determine the electron density, but combinations of certain lines give us the possibility to what we call electron density diagnostics that are independent of assumptions, for example, of the element abundances or other assumptions that we might make. So we look at ratios of different lines. And from that, we were able to find that the log of the electron density was very high. Normally in the corona, the density would be at about 10 to the 8. In an active region, it'd be about 10 to the 9. So we're really going up to very high densities here during the solar flare. Why do we need that? Because we need to calculate the energy content, and we need the electron density to calculate the energy and the temperature. So let me move on to SOHO. SOHO was perhaps one of the most elaborate and comprehensive solar observatories that we have had, because it had instruments which were designed to study the interior of the sun, helioseismology instruments. It had instruments designed for the surface of the sun, so looking at the photosphere and the magnetic field, and it had instruments to look at the atmosphere of the sun in the ultraviolet, and it also had a spectrometer on it, which is the one that it's probably, could we have the lights on at the back rather than the front, because otherwise I think it's difficult to see the slides. It was better, yeah. If you can you put them on at the back? Okay. It's okay? Yeah, it's better to see because I've got some movies coming and they're easier to see with the lights out, to be honest. They don't need to see me. Can see me later. And we had a coronagraph, so the sun is blocked here and we see material moving out. So fascinating project to work on. I was an investigator on the coronal diagnostic spectrometer because I'm a specialist in spectroscopy, but we worked together. We worked together as a team for that instrument, but we also all worked together to coordinate the observations from all the different instruments. And this was operated again at NASA's Goddard Space Flight Center. So I spent a lot of time there working with my colleagues, designing the observations, operating the different instruments and working together. So it was launched in 1995. Some of the instruments are still operating and the data from them is still being used, the coronagraph, for example. But some of the other instruments, we have better instruments now. So we've turned them off. It's wasting resources to keep them going when we have better instruments available. Now it orbits at the Lagrange point, and as we know, a DTR L1 will be going out to the same position. And that's the position between the sun and the Earth, where the gravity pull of the sun balances the gravity pull of the Earth. And it's about 1/100th of the distance between the Earth and the sun. And it orbits the sun with the Earth, so it sees the sun 24 hours a day. See the sun continuously. There are challenges because it's quite a long distance, and you've got challenges then with data downloads and communications. So it does bring its own challenges, but it also means that we see the sun continuously. So this is just video from the EUV EIT is called imaging telescope, which is around about, this is about 1 million degrees, or just maybe a little bit higher than 1 million degrees. And again, you can see it's ultraviolet, obviously. The sun is not green, but it's colored green. We colored different wavelength bands, different colors to distinguish them. You can see the coronal holes when the magnetic field goes out into space, is open, and the plasma has flown away. And you can see the active regions there where the sunspot regions are. And you can also see small brightenings all over the sun. And the sun's magnetic field, this is a measurement of the sun's magnetic fields, and you can see where the active regions are, where the magnetic flux is very strong. But you can also see all over the sun, small bipolar regions. And it was realized that actually that covering of the sun changes every 2 days with the magnetic carpet. As I said, in order to understand and analyze atomic spectra, you need a lot of atomic data. Now, everybody who wants to look at a particular spectral line doesn't want to have to go back through all the papers about that line, gather all the data together, and then decide which one they like or which one they don't. There's a lot of data. So what we did was we thought we'd make it easy for everyone to analyze the spectroscopic data and the imaging data. So we created a database called Chianti in Italy. This is from Arcetri. This is a team from Arcetri Observatory. This is us, Giulio, myself, Enrico, who now works in the USA, Ken in the USA, Massimo in Italy, and P.T. Young. And we created this database for everybody to use. And actually, everybody does now use it. Everybody in solar physics uses it, and a lot of people in astrophysics use it. Because it's relatively easy to use and it's freely available to everybody to use, it means that we now have many, many citations for it. And it's used to, when you're building an instrument, to predict what the intensities of the lines might be. And it's made in, if we didn't have atomic data, we would assess the atomic data and we update it regularly. This year will be another update. And if we don't have the atomic data, then we calculate it. And we make sure that what goes in there is reliable and accurate, and people don't have to worry about it. So as I say, it's freely available for everybody to use and regularly updated. So if we compare here, this is a spectrum from the coronal diagnostic spectrometer on SOHO. Plasmas against solar plasmas, even against stellar, solar spectra against stellar spectra. Make sure that it's accurate and the wavelengths are correct and everything about it is accurate. Another satellite that I worked on is called Hinode. And that was a joint Japanese, USA, UK, Europe as well mission. And it had an optical telescope for the surface of the sun. It had a spectrometer, which was looking at the atmosphere of corona, and it had an X-ray imager as well. So we were able to connect what was happening on the surface of the sun with what was happening higher up in the solar atmosphere. This was the principal investigator for this instrument I was working on, the spectrometer ICE, was Louise Hara at University College Mullard Space Science Laboratory. Hinode is still operating. Indeed, it's doing some very interesting work in collaboration with Solar Orbiter and Parker Solar Probe. With a spectrometer, it's a complex instrument, and you have to scan across a region. You don't get all of that image simultaneously. You have to scan, and it sometimes takes a little bit of time. But at each position along the slit, you get a spectrum. So it's a complex instrument, and we often have to combine it with observations with an imaging instrument in order to get the best results. This is a spectrum from the ICE spectrometer from 170 up to 284 angstroms. And again, you can see many different ion stages, elements, sulfur, iron, silicon. We need to be able to interpret those as they change. Here's a flare spectrum. This is a flare seen in different spectral lines. So you can see, we see the flare heating, we can see it cooling, we can see it changing. It's quite a small flare studied by Giulio Delzano. So if we take a loop, an active region, the foot points are anchored in the sunspot regions, and we want to understand what's heating and cooling those loops. And the process of magnetic reconnection is key to our understanding of how the corona is heated, because what we find is energy is transferred up from beneath the solar surface, up into the atmosphere, and then it is released when the magnetic field changes its configuration. So it can change its configuration on small scales, we call these nanoflares, small flares, or it can change its configuration dramatically on large scales, and then we'll get very big flares coming. So on small scales, we believe that this process, which was first proposed by Eugene Harper, where you take a loop, which is made up of lots of strands, but the foot point regions are moved around by convection because they're rooted in the convection zone. And what happens is that these strands get twisted up. And when they get twisted beyond a certain point, we get the magnetic energy is released and they go into a lower energy state, which is an untwisted state. So that was his proposal. And we now believe that this is quite key. And a lot of modelers have been testing out the whether or not this is the right proposal and doing it on different frequencies, high frequencies, low frequencies. As I said before, we can measure spectral line shifts, and this gives us motion towards us for the blue shift and away for us for the red shift. So this is an image from the EUV ICE instrument from Hinode. And here's an active region loop seen in iron 12 at 2 million. And this is what the shifted wavelengths look like. So this was quite a surprise for us because what we saw was there was downflows in the loops, but there was actually upflow regions in the outer parts of the active region. We now believe that there's a process called interchange reconnection, which happens quite high up, and this results in the outflows. Now, these outflows could well be connected with the solar wind, and that's still something that people are arguing and debating about. The AIA, SDO AIA instrument, launched in 2020, has provided us with a lot of observations and diagnostics. So if we look, it has different, it's an imaging instrument, but it has different channels, and each channel is sensitive, different wavelength channels, to a different temperature. So we can see all of these temperatures simultaneously with a cadence of 12 seconds. And from that, we're able to build models and connect for different features and see how well they connect. We combine 3 of these channels. We can see here the complexity, the open regions in the poles here, certain times, and then the complexity of the active regions. So you can take the magnetic field on the surface of the sun. The magnetic field in the corona is very, very difficult to measure, and that's what people are working on at the moment, trying to find ways to measure the magnetic field in the corona. VEL-C may be able to do that, and that's one of the things it's aiming to do. But we can also possibly use infrared lines to do that. But at the moment, you need to take the magnetic field in the photosphere and then extrapolate it using force-free usually. So we know that the fast solar wind is the source, comes from the coronal holes in the polar regions and also equatorial coronal holes. But then the challenge is, where do the other aspects of the solar wind come from? Here we can see a nice coronal loop as the sun rotates into view, observed with SDO-AIA. One piece of work that my student Sargam Malay worked on for her thesis was jets. So sometimes you get magnetic field erupting underneath the surface in small bipolar regions, and it will connect with the overlying magnetic field, and then you get a jet or very high speeds and often heating. So we've got models, and what we wanted to do was to connect the speed at which the material ejects out into space with the models. And I'll come back to that because these are thought to be quite important with regard to some features seen in the solar wind. Here she studied a jet which got very hot. We got emission up to 10 million degrees. So larger flares, of course, have been seen for a long time. In the visible, they were seen in 1859, and this is the drawing of Hodgson, Carrington and Hodgson, seen in 1859. And if that flare happened today, they think it was a very big one. It's an X class, and we classify a flare by the amount of X-ray radiation that comes out of it. So we go A, B, C, M for moderate, and then X for large, and then we go X, 1, 2, 3, 4, 5. This is thought to be a very large one. We've seen lots of flares with the Solar Dynamics Observatory more recently. The question is, if a large flare happened, how would that affect us here on Earth? As well as soft X-rays, we can also look at hard X-rays to look at the point at which the reconnection takes place and particles are accelerated. So here we have a flux rope erupting, and then behind it we get magnetic reconnection, and then we get particles or conduction energy fronts shooting down into the footprints of the loop. Here we see an image from TRACE, which is an ultraviolet observation. You can see the large loops growing, so we need to be able to model and understand those. We tracked some of these with different instruments, combining different instruments, and here we can see with AIA, the hottest channels come first, and then it cools off to the cooler channels, so we're able to track, this is the ghost flux, the X-ray flux. As the flux develops, we're able to track the temperature and see if that's consistent. Here's a map of the temperature at 10 million degrees. See temperature rises, falls again, electron density rises, falls again. And we're able to compare this with some of the models. HYDRAD is a code, a one-dimensional hydrodynamic code, which was developed by my student Steve Bradshaw, and people are still using extensively. And he was able, using the length of the loop and different features of the model, to be able to predict what the model would predict and see if this is consistent with the observation. So what we're trying to do is use the models and see how consistent these are with the observations. Another instrument called ARIS is looking at the transition region. This is also a spectrometer. So this is doing spectra in the transition region, and the magnesium lines, and some of the transition lines, carbon, sulfur. And my student, Vanessa Polito, now leads this group of ARIS and trains young workers to use the ARIS data. So she actually, as part of her thesis work, she also looked at this very high temperature line, this iron 21 line, which is formed at 10 million, and was able to see the shift as the chromospheric material evaporated into the loops, and the width of the line, which we think is due to some sort of turbulence. So I'm just going to move a little bit quicker because I want to get through some of these things, but this is from SOHO. We block out the sun and we see these coronal mass ejections, which you're familiar with. Billions of tons of material moving at thousands of kilometers per second. So here we could see material lifting off the sun, then shooting into space. If we make the sun even smaller, we can see it. This is from stereo. We can see it shooting way out into space. And of course, we're interested in modeling these and in understanding what triggers these coronal mass ejections. But we're also really interested in if they're coming towards us, what effect are they going to have on us here on Earth? Because besides the beautiful, so this is not to scale, of course, but here's the sun, here's a coronal mass ejection, and our Earth is obviously protected by its own magnetic field. But besides the beautiful aurora, and this is one seen from the International Space Station, other damaging effects that can harm astronauts in space. It can affect satellites, damage them. It can cause electricity blackouts or high-flying aircraft. So there's lots of other, because we now depend so much on technology, there are lots of other effects that we need to understand that connection between what's happening on the sun and the response of the Earth. As I said, at the moment, we're here. This is a Yoko image in the background, but here's the solar cycle, year along the bottom from 1990, 2020, and we're here now, 2023. And you can see, actually, we're getting quite close to the peak of solar activity there. So let's have a think about the solar wind. The solar wind was proposed long ago by Eddington. He was the first person to suggest the existence of a solar wind. Eugene Parker again in 1957 called it the solar wind, I think, and wrote a paper. He submitted a paper on the origins of the solar wind from the sun. A comet, you see two tails. One is the ionized tail, the blue one, and the other is the neutral tail. And that's what indicated that there was a solar wind flowing out from the sun, magnetized plasma. Eugene Parker submitted his paper to Astrophysical Journal, and that's what we do in science. We submit it, and then two or so referees will look at it and say whether or not they agree with it, and both referees rejected it. Now, they rejected it because it went against what was commonly thought at the time. However, the editor was Chandrasekhar, and he actually overruled the referees. He said there is nothing wrong with this paper. Mathematically, it is correct. Everything in it is correct. There's nothing wrong with it. So he overruled it, and it was published. And it is now probably the most important paper in solar wind theory. So if we look at the different components of the solar wind, we've got the fast solar wind coming from the coronal holes, which we understand quite well. We have the ejection of coronal mass ejections, which again has an impact on the Earth, quite severe. But we also have something called the slow solar wind, and that's intermittent. The element abundances change, and it can also have quite a dramatic effect on the Earth because it's not steady and it's not smooth. And it's this part, this slow solar wind, that people are focusing on to try and understand better at the moment. It's from the streamers around the active regions. So this is the launch of Parker Solar Probe in 2018, and here is Parker. Now, this is the first time, I think, that a satellite has been named after someone who is still living. Okay, normally give you that honor once you've passed away. But here he is watching the launch of his own satellite. And here's Nicky Fox, who is the principal investigator on Parker Solar Probe. Sadly, he's no longer with us, but he was there able to. Solar Orbiter was launched a little bit later in 2020, just before COVID struck. And the amazing thing is that it was operated from home computers. Okay, you can imagine what a complex operation it is to get the maneuvers right for the satellite, to test the instruments, and everything was done from home computers where they couldn't connect easily to the operations center, and everything was done precisely to time. So the commissioning phase was perfect, and then the science operations began. So Solar Orbiter and Parker Solar Probe are in unusual orbits. They need to go very close to the sun, and they need to use Venus to pull them in towards the sun. So Solar Orbiter has a 10-year mission phase and has already got some interesting observations from the sun. So if we compare the two, Parker Solar Probe stays in the ecliptic plane, where the Solar Orbiter goes out of the ecliptic plane and will be able to see the polar regions. Parker Solar Probe goes very close to the sun. It has to have special materials, of course, but it will go very close, 0.05 AU. That's the distance between the sun and the Earth. And it already has gone very close. Parker Solar Probe has in situ instruments, which are sampling the magnetic electric fields, energetic particles, detecting waves and shocks. But it doesn't have any instruments actually looking at the sun. It has instruments looking at the solar wind just off to the side of the sun. Solar Orbiter doesn't go quite as close as Parker Solar Probe. It goes to 0.3 AU, but it has both in situ instruments which sample the solar wind, and it has remote sensing instruments which are looking at the sun. So it's better able to connect what's being seen on the sun with what's being detected by other instruments on Solar Orbiter. It also has a spectrometer called SPICE, which of course interests me a lot. So these are some of the initial results from Solar Orbiter and Parker Solar Probe. And Solar Orbiter found these very small little brightenings all over the sun, looking in the UV wavelength of 170 angstroms around about iron 9, which is about 1 million degrees. Sees with very great spatial resolution. Here's a combination of just looking at the sun source regions and then extrapolating out, and you can see how complicated these features going out into the solar wind, particularly around the active regions, are. Parker Solar Probe identified something they called switchbacks in the magnetic field, and this is where the magnetic field seems to go back on itself in a sort of Z shape. And the origin of these switchbacks has been debated a lot, but it's thought these could come from those jets, the sort of jets that Sagan was studying, where you actually, magnetic field emerges from beneath the surface and it reconnects with the overlying fields and then causes these switchbacks. So one thing that both Parker Solar Probe and Solar Orbiter want to do is to trace the origin of the solar wind on the surface of the sun. So this is an area of intense study at the moment. The SPICE instrument is able to see all the spectral lines, which of course pleases me, but a lot of these spectral lines have different abundances. And from the abundances in the corona are not the same as the abundances in the photosphere. They're different in certain parts of the corona. And because of that, you're able to trace more easily where the solar wind is flowing. So parameters like the density and the temperature will change as the solar wind flows. But the abundances don't change. So if you put some ink into a flow of water, it stays the same. You'll see those abundances flowing in. So this is being used to actually determine the source region of the solar wind. And here is an instrument which samples the abundances. So this is an instrument sampling the abundances in the solar wind. So you're able to connect the two. A lot of work going on in that area. There's a hard X-ray instrument called STIX on board Solar Orbiter, and with the team at PRL, the Solar X-ray monitor, they've actually been working together with the STIX to combine the hard X-rays, the next fast flare they've seen, and the softer X-rays. And this is injection of coronal mass ejection seen from Solar Orbiter. Now, finally, I'm sorry, I'm running a little bit late here. I wanted to tell you about the work that I've been doing with the team at PRL, and this is very exciting for me, unexpected, but we have combined our expertise, Julio and I's expertise, with the technical and expertise at PRL to produce some very interesting results from the X-ray solar monitor. Now, you might wonder why we've got an X-ray solar monitor on board Chandrayaan-2, which is going to the moon, but actually what it's doing is monitoring the X-ray emission from the sun in order to understand the fluorescence from the moon. That's what I understand. So we're using the one to monitor the other. But of course, I'm interested primarily in the sun. It's a very sensitive instrument and with dynamic range here. So we're able to see both very small flares, and very large flares. And here's a quiet period of the sun, and you can see even during the quiet period of the sun, we've got a lot of small events. So this has been paper studied, published by Santosh and his group on this, looking during the quietest solar minimum that we've had, and all of these little brightenings. During an active region, when the sun rotates an active region on the sun, here we see a lot of dynamic activity and micro flaring activity, again, a quiet period and an active. Now, because it's a full disk instrument, it's actually quite difficult to determine where exactly this X-ray emission is coming from. So it's important, again, to combine this with another instrument, and this is combined with the Solar Dynamics Observatory observations. And during the early phase of the solar cycle, when it was just rising in activity, we were fortunate just to have maybe one active region on the solar disk. So we know that actually the emission here is coming from that particular active region. So we're able to combine the observations from Solar Dynamics Observatory with the observations that we're getting from XSM. So if we look from the X-ray spectrum here, up to 10 kiloelectron volts, we'll see that if we go in the quiet sun, it's this one here, this magenta, then we've got active region, then we've got a small flare, B-class flare here, the blue one, and we've got a C-class flare getting slightly bigger, and then we've got M-class flares. So you can see the big dynamic range that XSM has. And in addition to the continuum emission, we have these spectral features, which are for particular elements. Now, with the software that has been developed by the PRL group, we're able to determine lots of plasma properties. We're able to determine the emission measure, which I mentioned earlier. We're able to determine the element abundances of these different features for different ions. Temperature, peak temperature that reached. And what we've been doing is, in addition to taking the XSM, we've been using other instruments like Hinode XRT and Hinode ICE, and combining what we find with them with what we find from XSM, just to check that everything is consistent, and we find very good consistencies between the two. Now, I mentioned that the coronal abundances are not always the same as the photospheric abundance. So if you take the ratio of the coronal abundance to the photospheric abundance, relative abundances relative to hydrogen, what you'll find is that actually it depends on something called the first ionization potential. And this is the amount of energy required to go from neutral to the first ionization stage. And what happens is that the elements with the low first ionization potential, we call it a FIP, are actually enhanced in certain features in the solar corona. And this is because the acceleration mechanism up into the atmosphere depends on whether or not the plasma has been ionized. So if you just, or which layer it's coming from, if you just ionize a few elements, these are not necessarily ionized in the origin part. Now, this is a theoretical explanation for this. It's quite complex, but Martin Lamming has something called the ponderomotive force, which depends on the alphane waves bouncing from end to end of the loops. And then we get the first ionization potential developing. For example, in an active region loop, we'll find a FIP bias of about 3. So what we're able to do is what the PRL group has done, and we've supported them in some of this work, is we've looked at different flares. So this is the GOES, is another X-ray instrument, not as good and not as sensitive as XSM, but this is the GOES light curve, and this is the XSM light curve, the blue, and here we've got AIA 94, which is a high temperature line in the SDO channel, and 18. So selecting several of these events and flares and able to track them, find the peak temperature, emission measure, and abundances. And what we found is very interesting. We found a range of temperatures for these flares, depending on their size. This is a little bit of a busy plot, but let me see if I can explain it. Here's the temperature. This is for one particular flare, B-class flare. This is the temperature as a function of time. The gray curve in the background is the light curve for the X-ray emission. So this is the rise phase of the flare. And you can see the temperature is rising up to 7 million and then dropping back down. And here's the emission measure. That's also rising as the flare increases and drops back down again. But here we've got the element abundances of magnesium, aluminium, silicon, sulfur. The green curve here is the green line here is the photospheric abundances. And these lines up here, there's a range of them, are the coronal abundances, or abundances we find in the corona. Now, what we find happens is as the flare increases, the abundance decrease suddenly down to photospheric values. Hope you can see that as the temperature rises, the coronal abundances initially drop suddenly to photospheric abundances. They do it in all of these elements, they drop down. Now, what we believe is this is direct evidence for chromospheric evaporation. So we believe that material is coming up from the foot points of the loops. As the flare takes place, the energy is deposited down at the foot points, and this chromospheric evaporation is coming up with photospheric abundances. So this is in our 2021 paper and described in more detail. We haven't quite explained the characteristic that it actually returns to coronal abundances. You see it returns here, and it returns quite quickly. We're not too sure why it returns so quickly. But for me, this was really, really exciting, because I think, although we've seen blue shifts and other evidence, this is, to me, is the first direct evidence that we have this process called chromospheric evaporation, where material is coming up from the lower layers of the solar atmosphere into those loops during the very early, we call it impulsive, the early stages of the flare. We've done, as I say, I won't go into details because I'm running out of space. We've done comparisons with the temperatures and densities, etc., emission measures we get from other instruments from Hinode, and we've tracked the temperature changes here with AIA and compared them, and then got an emission measure and fed it back through the XSM to make sure consistency. We're all the time making sure what we're doing is consistent and what we're getting, the results we're getting are accurate and reliable. And we're doing that by doing comparisons with other instruments. Very exciting work, and I'm very happy to be involved with it. Thank you, Santosh, and the other members of your group for including me in that. It was unexpected towards the end of my career, and I'm very happy to have worked with you. So, besides working with Santosh and his group at PRL, it's been a great honour to work with Durgesh Tripathi here at IUCA over the years, and to interact with his students, his Sargam and his other students. And I regular visit to IUCA, maybe visit once a year there, and I've interacted not just with his research group, but with other students at Ferguson College and other places, and also at school with school children and with teachers. And recently I was working with a group of 150 just last week.
No, because it was launched.
Huh?
I'm saying there is probably needs of updation at the launching of this one.
Oh, sorry. Yes, I'm sorry. I didn't update that slide. I should update that slide. Sorry. Yes, of course. Sorry, I replaced the slide and I forgot to update it. I watched the launch of Aditya L1 in September. I hope you did too. It was very exciting. I think it was 2nd of September. And it was not just news here in India, it was news around the world. So in England, and I was asked to comment for New Scientist on the launch, not just the landing of the lunar module, which was again a huge success for ISRO and for India. And again, Santosh's group and PRL have been involved in the instruments on the lunar landing, but the launch of Aditya L1. In fact, I was at IUCA last week, and we've just, Durgesh's group leads one of the instruments called Suit, this instrument here, and they were testing that out last week. So I don't have time to go into all the details of Aditya L1, and forgive me for getting the wrong slide in there, but they are all being tested at the moment, although to make sure that in early January, they'll be ready to watch out for all the publicity and the data, the science. So the early stages of testing an instrument is called the commissioning phase, and then the science observations will begin in earnest. This is my last slide, you'll be glad to hear. This is the project that was mentioned earlier, working with schools and young people in the UK, where I have a team of scientists and artists working together to go into schools to interest students, both in science and the arts, because I believe that creativity, innovation is key to our future, and that we need to work together in that regard. So we engage students in sciences and get them thinking and get them asking questions. And then the feedback has been superb, that they really enjoy engaging in that way. So thank you. I'm sorry to kept you so long.
Thank you, Helen. Thank you for a very nice lecture. So there will be question.
Yeah, this was really enjoyable talk because you covered all the way from the Yoko time to the recent times. It's interesting to see that most of these spacecrafts, solar observatories in space, they had been observing. I mean, they were planned to observe mostly from ecliptic planes, except for the solar orbiter,
Yes.
which was launched in 2020. And I think that is the only effort after the Ulysses, which
Ulysses.
gave the velocity variation with latitude of the sun.
Correct. Yes.
So I would have liked if you could probably give some, important results which came out from Arvind about, the
Orbiter hasn't gone out of the ecliptic yet. Oh, it'll take a while. It's still in the ecliptic plane at the moment. It will gradually go higher and higher. So you'll have to wait for the results.
not yet.
It has not yet gone out of the ecliptic. The aim is that the orbit
That takes some time when
it takes some time to get out of the ecliptic, maybe a year.
Twitter and gets probably the speed tour.
It's going to, it's getting the catapult effect from Venus. So, but it will take, at the moment, it's still orbiting in the ecliptic. So we don't have those results yet, but the idea is to see the magnetic field close. It won't go over the polar regions. Ulysses was mentioned, and Ulysses was a sampling instrument, and that went over the polar regions. Solar orbiter will go higher in latitude, but it's not going to go right over the polar regions.
So this will observe the polar region magnetic fields and orbiter.
At an angle, yes. Yes, yes.
So when is this expected to?
I'm estimating it'll be about a year or so, but I'd need to check that.
Madam, there are three evolution processes. One is the solar flare, solar wind, and also prominence. The mechanism is same or different for all these processes.
Solar flare, what was the second one?
Solar flare, solar wind, and prominence. You have been.
Solar wind, okay. Yes, of course, they are very connected, and I haven't touched on prominences, filaments. But when you get the solar flare, you get a filament eruption. So the magnetic flux rope develops gradually, gets gradually more complex. Sometimes you see this sigmoid structure in the X-rays, and then will erupt. So the filament or the prominence is an important feature in the active region, but you can also get it erupting in quieter regions in the sun and going out and causing coronal mass ejections, etc. But definitely the prominences, and in fact, at the moment, there's a lot of work going on about condensation, that you see coronal rain, cooler material. So the connection between the prominences and the magnetic structures and the evolution of the magnetic field in the active region are interconnected. But you're quite right, I didn't really mention the importance of prominences.
Also the formation of the sunspot Not due to only magnetic or any other reasons.
Well, rotation and magnetic fields, and I'm not an expert on sunspots, but I believe you often see their emergence, but you also see their rotation of the sunspots as they become more and more complex. I'm sure other people here could answer that question better than I
My
could.
last question is, the temperature of corona is very high.
Yeah.
So the comparison to the photosphere.
Yeah.
What is the reason of this?
Well, I say
Sorry.
yes, the general process is that the energy is channeled up from beneath the surface. It's believed to be channeled through the magnetic fields, but then it's a question, how is it released? So that process that I mentioned called nanoflares, where Parker proposed, where you get the flux tubes twisted, that's one proposal for heating higher up. Other people believe that, and I haven't mentioned them, that waves are an important process for channeling energy up from beneath the surface too. And so people are investigating little nanoflare processes and waves.
Sorry. In the solar magnetic, so earth magnetic field is due to the presence of the iron and etc. on the earth. So, but in the sun there is a 90 or about 80% are the hydrogen. So how it is possible the generation of the solar magnetic field in the sun?
Well, there's 90% hydrogen, then there's helium, then there's trace elements of others. But it's because you've got a ionized plasma and motion. So it's like it's called a dynamo effect, and it's formed.
So it is generation outside the interior, not in the.
It's formed in the interior. Some people think, and I'm not sure what the present stage of this. There's a layer between the radiative zone and the convection zone called the tachocline, where the shear is very great, and some people think it might be formed there. But when it's formed beneath the surface of the sun, and then it erupts out through the surface of the sun.
At the sun, is it correct that the spectra is dominated by the visible rays?
Say it again.
At the sun,
Yeah.
is it correct that the spectra is dominated by the visible rays?
Yes. Yeah. Is the spectrum of the sun dominated by the visible range? The sun is white. So basically, the light coming from the visible will dominate the sun's radiation. But as I showed with that X-ray picture, the white light, it's called the total irradiance of all wavelengths of coming from the sun. It doesn't change dramatically. It changes a small amount during solar cycle from quiet to active, but actually the X-ray emission and the ultraviolet light changes dramatically during a quiet period and an active period. And of course, the ultraviolet light affects the upper layers of the atmosphere of the Earth as well. It affects the composition of the Earth. And we need to understand that a little better. So there's a lot of focus on what we call irradiance, the amount of radiation coming from the sun. And in fact, SUIT instrument, one of its objectives is to study the irradiance in the ultraviolet. So it's actually, and there's no instrument actually doing that at the moment. So it's going to do some important work in that. Have you got some questions online?
Yeah, just check.
Are there any questions online?
Say it again.
Sun maximum.
You said it again, sorry.
What
happens? What happens after the solar? And when the magnetic energy goes down? Yeah? No question. It's okay.
So what she's asking, what happens after flood maximum? So
It will go down again. So it's dissipated. So the magnetic field is going up.
11 years, why this lot of 5 years, 10 years, 12 years?
Nobody knows. It's not, the cycle of 11 years is, as far as I know, has not been explained. One thing you can do is you can look at other stars that have different rotation periods. They also have stellar cycles. So you could put the sun in the context of other stars and see if you can get some information from that. But as far as I'm aware, nobody can explain exactly why it's 11 years. Does anybody else? Is that correct, Nadita?
Sure.
Yeah, okay. So the other stars have cycles, but they have different cycle lengths and they have different rotation rates. So slightly different, yes. It's not, although it's 11 years on average, there are other longer period cycles in that as well.
It's a question from YouTube.
Yeah.
You can take it. So, if solar UV radiation is delayed relative to solar X-ray emission,
Is the solar UV related to the X-ray?
it's delayed.
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 Whether there is a time delay between the UV and the X-ray.
Yes, yes. I understand. I think during a flare, you mean, or?
Yeah.
During a flare, the X-ray rises very, very quickly in the impulsive phase. But also, in fact, the ultraviolet in certain lines, in transition region lines, also rises very quickly during the impulsive phase. So it's not automatic that it's delayed, although what happens then is after the initial stage of the flare, the X-ray reaches high values more slowly. It's called the thermal phase of the flare. And then it gets very hot, so it gets to 10 million. And then it will be emitting very strongly in the X-rays and the ultraviolet won't be so strong. But then as it cools down, it may also then, the ultraviolet may rise up for a longer period of time. So it's a little bit complex. Yeah.
So there is another question. What I understood is what is the duration of a typical CME?
The duration of a CME, I'm not quite sure what that means. Duration, it depends on the speed at which it leaves the sun, which can be hundreds of kilometers per second to 1,000 kilometers per second. So the duration from when it's initially ejected, duration going out into space would be perhaps it means to get to the Earth. The time it takes to get to the Earth would be on average about 3 days, perhaps. But if it was going very fast, it might come a little earlier than that, or if it was a little slower. So it depends on its speed, and that's obviously what people are trying to measure and then track them in the solar wind. But the fast particles from a flare, very energetic particles, could come a lot sooner. So they could come within hours. But the CME would typically take maybe 3 days, 2 to 3 days to reach the Earth. Yeah. So if you see a CME and it's coming in the right direction, coming towards us, then you can expect that depending on the magnetic fields and things, expect you might have geomagnetic activity and aurora maybe 2 to 3 days later. So there's lots of space weather sites that predict this. And obviously we try to make those predictions more accurate by understanding what's happening on the sun and how it transits towards the Earth.
So if there are no more questions from the audience, we can take up the questions from the next.
Observations at L1 Lagrange.
Yes, there are. Do you mean to have something at L1 and then something on the Earth? Or,
Yes.
there was a satellite I briefly mentioned called Stereo. Okay, and that was 2 satellites, in fact.
Yeah.
Started off from the Earth and then went in the same orbit as the Earth, but apart, so that they got a 3-dimensional view of the sun. And the advantage of that is that you can then see the speed of the coronal mass ejections. If you're just looking from the Earth vantage point, you'll see like a halo, but it's not so easy to measure the speed. If you put a satellite not in the Earth sun direction, but somewhere else, then you can actually, and some people want to put satellites in something called L5 point, which you would then see the coronal mass ejections coming from the sun to the Earth, and you can measure their speed more accurately. We were just talking about the star. SOHO, the Aditya L1 will be in the line of the Earth and the sun. So the advantage for it is that it sees the sun 24 hours a day, but it won't give any advantage with regard to seeing different angles on the sun. Do you take the one there? Any more questions online?
No, I think we can now take the questions on WebEx. So if anyone has a question on WebEx, please unmute yourself and go ahead and ask your question.
Can they hear?
You can unmute yourself. Those who join on WebEx can unmute themselves and ask Helen their questions.
I'm very shy.
Probably. Or hungry.
Hungry, yes, sorry, I'm probably ready for their dinner. I'm sorry to have kept you so late. I know it's getting late in the day. We're all tired.
Okay. There are some interesting talks which go up to 6.
Okay. Does anybody else in the room have any other questions? Yes, please. Yeah.
According to you, what point of resolution would be needed in observations or anticipated observations and POB observations to say with confidence that this would be able to?
Yes, well, they've tried lots of different flare frequencies, and I think one of the ones that people like Peter Cargill and Jim Klimchuk have done a lot of work on this and looking at spacing between nanoflares. But I think one of the ones that seems to be quite good is like bunching of nanoflares. So you have a bunch of nanoflares and then you have another bunch of, so that one, Peter Cargill has some papers about that, which, and they match the so every 2 years for the last 20 years, we've had something called a loops meeting. We have it around different parts of Europe, and all the theoreticians and all the observers get together and they argue about which model suits the data best using the parameters. But I think Peter Cargill is probably winning at the moment with his most recent models, and they seem to be able to reproduce what's observed in the ultraviolet quite well. And I think the other thing they recognized is that besides the heating, there's also plasma cooling. So we get condensation. So there's a constant flow. So that's important as well. So that's been studied a lot as well, cooling loops.
I don't see anyone joining us from WebEx or asking any questions. So,
okay.
Arvind, I think we know.
Okay, so if you have no more questions, let us thank the speaker.
Thank you.
And I have another announcement to make that we have some refreshment at our canteen. We will right now, but let me have Bhuvan first, call Bhuvan for delivering his vote of thanks.
Any.
Thank you, Ramesh. So I feel honored and privileged to get this opportunity to propose a vote of thanks on this very special occasion of the third Dr. Arvind Bhatnagar Memorial Lecture. First and foremost, I convey deep regards and hearty thanks to our speaker, a renowned solar scientist, Professor Helen Maison, for kindly accepting our invitation and gracing this occasion. It was indeed great to listen to you. You gave a very amazing and very mesmerizing lecture, reaching for the sun. Thanks again for your presence today and delivering this lecture. So before I proceed further, I would like to request Head USU, Professor Shibu Matthew. So to present a memento to Professor Helen Maison in appreciation of her presence today here as a speaker of this event.
very much. I will treasure this.
Thank you. I express my gratitude to our director, Professor Anil Bharadwaj, for his encouragement and invaluable support in the organization of this lecture series. He has always been a source of motivation and provides new and very useful ideas, and this event is no exception. Thank you, sir. I would like to thank entire audience for attending this program, both in online and offline mode. And as we said earlier, so this is the third lecture in this lecture series, and the first two lectures were in online mode because of the COVID restrictions. And this time we are having it in offline mode, so we are really happy about it. I can see many of my colleagues, faculty members, researchers, and students from various prestigious organizations of Udaipur, Mohanlal Sukhadia University, BN University, and RNT PG College. So thank you very much for coming here and gracing this occasion. Also, I take this opportunity to thank all those who are attending this event online, because I saw that many of us were attending this event in online mode from outside PRL. And I also take this opportunity to request them to subscribe our PRL's YouTube channel for various events like PRL Ka Amrit Vyakhyan and PRL Amrit Rajbhasha Vyakhyan and various other scientific events and other activities. I thank Professor D. Pallam Raju, Dean PRL, Professor R.D. Deshpande, Registrar PRL, and Professor Shibu Matthew, Head USO, for their various role towards successfully organizing this event. I'm also thankful to all the members of Dr. Arvind Bhatnagar Memorial Lecture Committee who gave us various useful suggestions. I also thank my senior colleagues, Professor Nandita Srivastava, Professor Santosh Vadavale, Professor Ramit Bhattacharya, for playing important role in planning and preparing this important event. And I also thank all the USO colleagues who coordinated various activities toward organizing this lecture. So with this, we close today's program. Now I request all of you to assemble outside for a group photograph. And after the group photograph, we will go to USO canteen for a high tea. So thank you very much again. Bye-bye.